In the final session, we will be talking about some examples. In particular, we focus on the volcano dataset. Before going to the volcano dataset, I'll talk a little bit more about extremes and its relation to point processes. It provides us with a nice general framework in studying both the time as well as the magnitude of these events. So why consider point processes? Basically, what we're dealing here with, things like earthquakes and volcanoes, are sort of discrete events in time. They have a certain magnitude and they occur at a certain time. So if you just for a moment don't think about the magnitudes, but just at the time by which these occur, then these occur at certain discrete times. And so in mathematics, and particularly in probability theory, these events are described what we call point processes. Point refers to a single instance in time, and a process refers to the fact that we can describe this with some kind of probabilistic or stochastic model. So what will enable us to do is that it'll enable us to link time with magnitude. We should, however, note that not all of the extreme events that we're interested in are things that occur in time, although there are many of those, of course, such as floods and earthquakes and volcanoes. Diamonds is another example where time is not necessarily something that is occurring. And diamonds, actually, what we have is space. You could imagine that a diamond deposits is basically a set of stones, discrete points with a certain attached with it a certain value or size, but are distributed in 3D space. So again, there we could potentially go to a space, a magnitude, 3D space magnitude process, where we have something that's occurring in space and has a certain magnitude. Okay, let's first start with some background on point processes in general. So a point process, here's the realization of a point process. It's essentially a discrete set of points distributed in space. And so here what we have is a realization of a Poisson process, simply because the way these points are distributed are completely random. The fact that they're random does not mean that by accident there could be some clustering, right? So that's the same as drawing samples from a normal distribution. By accident, you may have a few samples that are close together. What we're often interested in this point process is counting, or the counting distributions. So counting distribution basically means that I take some subset A of the entire area. Let's say I take a block over here or a block over there, and have that block has a certain size. I'm interested in the number of points in this block. For example, this is quite important when we're dealing with diamond deposits, because diamond deposits are essentially a number of discrete points or stones that are distributed in space. They're not distributed as a Poisson process, but it's something that can be described by a point process. So what we're then interested in, of course, is the number of stones within a certain area, because I may be excavating this block here and I would like to know how many stones there are. Since, of course, I do not know the underlying exact distribution, but I could assume something about the nature of the distribution, such as they are independently or they're randomly distributed, then I will arrive at some probability distribution for this n of A. A couple definitions here. First of all, we'll define the intensity measure, which is the expected value of n of A, and of course that is itself a function of A. So on average, we expect more stones in a bigger area than a smaller area. So that leads us then eventually to the definition of the homogeneous Poisson process. So a homogeneous Poisson process is basically, as I stated before, it's a random collection of points in an area. And what's characteristic of that process and resulting of that process is that the probability distribution of number of points in a particular area A has always the same shape regardless of A. So here A could be a time interval, but it doesn't have to be a time interval. It could also be a set of points within a block. And so the kind of distribution we have is e to the minus lambda. So lambda is this intensity measure, as is the expected number, and then this is the size of A. So in this case, if it's a time interval, it would be T2 minus T1 if T2 is larger than T1. And so lambda times 2 and so on, you have here exponent I, etc. So this is nice. That means depending, irrespective of the size of A, I always get back to shape. It's just that the size of A is a parameter of this distribution. Another important point is that, and this is the direct result of the independence of the random distribution, is that the number of points in an area A and the number of points in area B are independent random variables as long as the A and B are not overlapping. And that makes a lot of sense too, right? Because if A and B were to be overlapping, then at least they have that overlap in common, and that would then create a dependency. Of course, the Poisson process is a quite idealized case. In so many cases, we don't have this ideal process. In that case, we will model the distribution of points using what is called a non-homogeneous Poisson process. So this is an example of a realization of a non-homogeneous Poisson process. It basically means that the intensity measure that we previously saw as constant is no longer constant, either over space or time. So here we notice clearly that the intensity measure is probably constant when looking in this direction, but it's no longer constant when looking in this direction. So this intensity measure lambda is now a function of x. X would be that particular direction. So the number of points in an A is now no longer homogeneous. It means that the number of points in this area, if I take a block in this area or a block in that area, will clearly be very different. And so their distributions will be different as well. And so the way a non-homogeneous Poisson process works is that we look at the number of points in an area as a Poisson process, but now with a varying lambda, and the lambda is essentially the integration of the lambda that we have as varying our space. So for example, if I would look at the point process over this block here, I would have to integrate over that lambda over x over that interval, and that gives me that new intensity measure, and that I'll plug into that equation that I had in the previous slide. So what does this all have to do with extremes, you would ask? Well, let's get back to our volcano data set, and remember that the way this data was created was by observations, and so obviously some observations reported from literature, calculated from data, calculated from observations, and some are just directly observed. And in particular, in the record, we have more preservation of volcano eruptions or just direct observations over the last, say, 2,000 years compared to all in the Holocene compared to the other 8,000 years before that. And so it's clear that if you compare that with the previous slide, is that we now have, again, we can see this graph now as a point process, but the point process is not over, say, y and x. It's basically over time and magnitude. So basically what we're going to do is creating a new space that's the time magnitude space, and in that space we will assume things or have some kind of point process, because each eruption has a certain magnitude and occurs at a certain time. So what we notice clearly, as in the previous slide, is that our process is not homogeneous, that it seems to be got more points over here than over there. But it does seem that if we go to the higher values, that we seem to have something that seems to be relatively Poisson. And so one of the things that we'll do later with the kind of models that we'll be developing is to also develop a model of underreporting. And underreporting simply meaning that certain eruptions are not always observed, and so they're only observed with a certain chance or probability. Okay, so here's a few theoretical results. So we're not going to go into derivation because that's a similar derivation as for the extreme value, generalized extreme value distributions. So I mentioned before that we'll be looking at the time magnitude space here, MT. And for sake of generality, I'll be assuming I'm studying a certain beginning of time and end of time, and I'll call beginning of time 0 and end of time 1. That's something that the standardization that we'll be doing later. So again, I describe observations, right, that I have within that time. So I have observations of basically x and t. And so what I'd be interested in is what happens when this threshold, so I've taken a certain threshold here, what happens if this threshold goes up? What kind of distributions do I then get? So, and that's then again described by the particular extreme value distributions. So again, I look at a sort of form of standardization. Remember, these a_n and b_n are similar normalization constants that I had used before. I'm looking at the magnitude observations standardized by these. So what's the probability that these then are element of some omega? That means basically this, if this is omega defined by this threshold and the time interval, then extreme value statistics or the probability theory shows that this probability is essentially of this form here. And so again, in this form, we see a number of things appearing that we've seen before. First of all, there's this extreme value index, so this rate of decay, as we could say here, that is telling us something about the shape of this probability distribution. There's a mean and a variance, and of course, there's also the threshold. So if we now look at a number of observation n, and assuming that that number of observation over some a is binomially distributed, so we're looking at here is the occurrence of some yes or no discrete event where each event has probability p occurrence. And we also know from statistics or from probability theory that if n goes larger, n goes to infinity, then this binomial distribution becomes a Poisson distribution. And so the Poisson distribution is described by the intensity lambda. And so this lambda is again described, this intensity, that number, average number of points, is described by this the same kind of shape as we've seen before. So that is for when the time is between 0 and 1. If the time is not for a general time interval, then we just multiply by t2 minus t1. So that gives us something unique, right? As it gives us something more general than we had before, because now we are looking directly at the intensity process as a function. So the time as intensity for us is as a function of this form of the extreme value form. Okay, so well, we've seen a lot of theory, and so we're now ready to do some real applications and look at some real data and see how well extreme value statistics actually does in making predictions. So we return to the same data set as before, and what we'll do is we first look at the shorter period, actually where we only have direct observations, for example, say starting 250 years ago, and use that data set, and then we'll look at the entire data set where there's clearly underreporting. So how do we actually model underreporting, and how can we see whether or not underreporting occurs? Well, in statistics or in probability, the way we do that is we build a model for in the case where there's no underreporting, and then we'll build a model in the case which has underreporting, and then we'll have some underreporting parameters, and then we estimate those parameters and see whether or not they are, say, different from 0, which would be the not underreporting case. So again, imagine I have n samples, and those consist basically of a time and a magnitude. So if there's no underreporting, then obviously I will have follow a Poisson process, and that Poisson process, remember, was described by a intensity measure, and that intensity measure is in its standardized time interval where you have that value of xi, which is the essentially the extreme value index. So you probably wonder, how do we find all these parameters? Again, there are many methods. I'm going to go into the methods itself. One is to do is simply use maximum likelihood. So you formulate a likelihood distribution, which is then a function of the data as well as the 3 parameters, and that's a specific form of this likelihood distribution. Again, I will not go into that, but you notice here that that if we have Poisson, we can assume independence, and so we get basically this lambda evaluated into the data, which is then a function of the parameters. So once I've estimated the parameters, mu, sigma, and psi, then I can calculate annual rates of exceedance or return periods, which have these closed form expressions as shown here. So when you do have underreporting, then we'll look at a model for underreporting. So it basically means that my underreporting intensity is a function of the no underreporting intensity times some probability. It's basically saying that a model for underreporting means that things are observed, but only observed with probability. So in case of no underreporting, this probability is 1 for each of the single observation. So there are some restrictions, of course, on what this P of T of X can be. First of all, if T goes to 0, it should increase. That means the underreporting will essentially decrease as we get more and more to the present. Also, this should be a non-decreasing function of X. That means as X it goes up, then the threshold goes up, then essentially the amount of underreporting will go up. So my larger events have less probability of underreporting than smaller events, and so on. There's a couple of other constraints as we come up with some kind of a parametric form, which is explained here. Yeah, so yeah, I forgot to mention essentially that P of 1 is basically the probability of the present. So in the present, there's no underreporting, and so that just increases towards the present. So now we have introduced basically 3 more parameters, which is this rate of underreporting, then W and V are essentially these magnitudes that are introduced. And so again, now we have a model that consists of 3 extreme value parameters, mu, sigma, and psi, as well as 3 underreporting parameters. We can also simplify this model by taking u as 1. There are many alternatives to this. Okay, so let's first look at the modern data set, say from 1750 till now, where if you look at this graph, it doesn't look as much underreporting, at least that doesn't look very clear to me. And so we can just proceed with extreme value statistics by estimating mu, sigma, and psi. So you notice here that that estimate is a function of threshold. And that's the discussion we had in the peak over threshold methods, where we said that the choice of a threshold is quite important. Choice of a threshold is basically telling you how much data you take over that threshold in order to do your estimation. So here we take, if the threshold is 4, then I've estimated essentially that parameter mu to say between approximately 2, let's say, using all the data that's above the threshold 4. And so, of course, what we get is as the threshold increases, we get less data, and so the confidence intervals will become wider. So here I'm pretty confident. Here I'm not confident at all. And then here that's basically the mu and the sigma. What's the most important parameter, of course, is this psi, the extreme value index. So what we expect to happen with the extreme value index is that the extreme values will certainly not should be negative. Well, why do I say that? Because a negative extreme value index means that there's an endpoint. There's a magnitude of earthquake that cannot be exceeded, and that sort of makes sense, right? So it makes sense in the sense that we expect that there be a finite maximum, that infinity is not a possible earthquake size, so or magnitude. So obviously, if psi is 0 or above 0 in particular, then I expect that there will be that infinity will be the maximum, and so that seems physically unrealistic. What we notice also is the instability of psi as I increase the threshold. Actually, you can see that psi even becomes positive, and so with some probability, if I would take this threshold here, I get positive. I increase the threshold, you get this variance that's occurring. That's the variance we saw in the peak over threshold methods when we started decreasing the amount of samples as we started estimating the extreme value index. Okay, so then I can do some analysis of return periods, so that once I have mu, sigma, and psi, I can put that into the return values, so return level versus return plot, and I get, just like with the case we saw with the daily rainfall, I get a fit, and I also get some confidence interval. Since for phi, when when I take a threshold over 4, then I get a negative xi. Negative xi means that I actually have a sort of an endpoint, we call that, and the endpoint in this case is 7.51. So this basically means that based on my data analysis, I can never get a predicted magnitude of 7.51. Of course, that itself has its own confidence limits, and I think they are shown over here, right? So these are confidence limits over the predicted magnitude level. This is something funny here in the sense that I do have the lower confidence limits is not quite correct, obviously, because I do have observation above this lower confidence magnitude. So that also means that the confidence limits we calculate here, or the method that's been used is probably not the right method, and that maybe other methods are more appropriate. So one thing that we should note is that that in history there has been essentially a very large magnitude, which has been the Fish Canyon tuff eruption. So that's this magnitude here of above 9, and so it's clear that with this threshold, my model is not predicting very well this largest magnitude, and we'll come back to that later. So in case I increase the threshold, then it seems like I'm starting to get into the confidence limit starts to be capturing that very large value. I did forget to mention in the previous slide that the fish tuft magnitude is actually collected from analysis based on 36 million years, and so that's not in our Holocene period. And so even though they are calculated values or estimated values, it still seems there's a disconnect between our data and the maximum. So if we now consider the entire Holocene, so now clearly we have underreporting, and so we have to have an underreporting model into our data set. So here are the results. The top part are again parameter estimates dependent on thresholds, and the top part we have mu sigma and the rate decay, and at the bottom we have the V, the W, and the P. And so what we notice is that the VW basically are 0, but that there is indeed an effect of underreporting, and that of course depends itself on that the timing, right? So we have a dependence on timing, so that's the timing axis. That we have a dependency, we clearly saw that was a non-homogeneous Poisson process, and so there's some kind of a rate. Rate of reporting that increases with time, and that's that time period here essentially, or that rate, which is a power law. And so then same for the we see the similar results for as previously, and now what's a bit nicer is that I do seem to have quite negative, or have negative values for more thresholds, and it's pretty likely that indeed our data set has a finite maximum that we can estimate again. So again, we're looking at return periods, and so again run into the same problem, which is that the predicted magnitude limit is much larger, is essentially very different from this actual observed maximum. And so there are a couple of explanations we can give, and one obvious explanation is that it could be that we don't just have enough data, period. That maybe it's not because we have enough data to make confident predictions, it's because we have possibly not observed certain types of volcano eruptions, or the physics of those volcano eruptions is very large volcano eruptions. It may be very different from the physics of say, volcano eruptions above magnitude 7. And so if that's the case, then no statistical model will be able to predict that. And so we'll have to build physical models in order to build these very large very large volcano eruptions. Okay, so that's the end. For diamonds, there will be an assignment, and so I refer to the assignments for that. Thanks for listening.